Private service connectivity across clouds. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. In this series, we're going to do a detailed side-by-side comparison of private service connectivity across the three major cloud providers: Google Cloud Platform, Amazon AWS, and Microsoft Azure. Each of these platforms has developed its own mechanism for allowing services to be consumed privately, without traffic traversing the public internet. The capability we're examining goes by different names on each platform. On GCP it's called Private Service Connect. On AWS it's called Private Link. On Azure it's called Private Link. Despite the similar branding on AWS and Azure, these three implementations have meaningful architectural differences in how they establish connectivity, what constructs they expose, and what scenarios they support. By the end of this series, you'll understand not just the mechanics of each solution, but the trade-offs that should drive your architectural decisions when operating in multi-cloud or hybrid environments, or when evaluating which platform best suits your service consumption patterns. GCP Private Service Connect Core Architecture. Google Cloud's Private Service Connect, commonly abbreviated as PSC, was introduced to give both Google-managed services and third-party services a uniform private access mechanism. PSC operates at Layer 4 using forwarding rules and internal IP addresses, meaning connectivity is established via TCP and UDP at the network level rather than through a proxy or application gateway. Let me walk you through this architecture diagram in full detail. The diagram illustrates how PSC connects a service producer VPC to a service consumer VPC using Google CP's private network infrastructure. Starting with the service producer VPC on the left side of the flow. This is the organization that owns and operates the service. Within this VPC, there is a backend service, which represents the actual workload and application, a PI, or managed platform that the producer wants to expose privately. The backend service sits behind an internal load balancer, which is a regional, internal Layer 4 or Layer 7 load balancer that distributes traffic across backend instances. The internal load balancer does not have a public IP address, it is purely internal to the producer VPC. The critical PSC-specific construct on the producer side is the service attachment. The service attachment is a PSC resource that the service producer creates to make their load balancer's forwarding rule accessible to other projects and organizations. Think of it as a published listing for the service. The service attachment has a URI that consumers reference when they want to connect. The producer can configure the service attachment to either auto-accept all connection requests or require explicit approval per consumer project. On the consumer side, the consumer creates a PSC endpoint within their own VPC. This endpoint is a regional internal IP address that the consumer allocates from their own VPC subnet. GCP then creates a forwarding rule that maps this private IP to the producer's service attachment. From the consumer application's perspective, it connects to a normal internal IP address within its own VPC. There is no routing complexity, no VPC peering, and no awareness of the producer's network topology. Google CP's network fabric handles the NAT translation transparently, ensuring that the consumer's source IP is preserved in a way the producer can observe, while also ensuring the producer's internal IP space remains completely hidden from the consumer. Google CP PSC connection approval and DNS integration. Two operational aspects of Google CP Private Service Connect that deserve detailed attention are the connection approval workflow and the DNS integration model. Both of these directly affect how service producers and consumers manage their relationship and how consumers resolve the private endpoint. On the connection approval side, when a service producer creates a service attachment, they choose between two acceptance policies. The first is automatic acceptance, where any consumer project that creates a PSC endpoint referencing this service attachment is immediately granted connectivity. This is appropriate for internal platform services within a single organization. The second is explicit acceptance, where each consumer connection request is queued for manual review by the producer. The producer can then accept or reject specific connection requests based on the consumer's project ID. This is critical for commercial software as a service scenarios where the producer needs to enforce licensing and entitlement. The diagram walks through this connection approval flow. The consumer project sends a connect request to the service attachment, which immediately moves the connection to a pending state. The service producer then reviews the request and makes an accept or reject decision. If accepted, the PSC endpoint becomes active and the consumer application can now reach the service via the private endpoint IP. If rejected, the connection remains in a rejected state and the consumer must investigate before retrying. On the DNS side, GCP does not automatically create DNS entries when a PSC endpoint is provisioned. The consumer is responsible for creating a private DNS zone in Cloud DNS that maps a service hostname to the PSC endpoint's internal IP address. For example, if the producer's service is accessible at a pi.partnerdomain.com, the consumer would create a Cloud DNS private zone for partnerdomain.com within their VPC with an A record pointing to the PSC endpoint IP. This ensures that when consumer workloads resolve a pi.partnerdomain.com, they receive the private endpoint IP rather than the public IP. AWS Private Link Endpoint Services and AWS Marketplace Integration. One of AWS Private Link's most commercially significant features is its deep integration with AWS Marketplace. Service providers can list their private link-backed services on AWS Marketplace, making private consumption available to any AWS customer without requiring custom contracting or complex network arrangements. This has made Private Link the dominant mechanism for software as a service delivery on AWS. The diagram illustrates how Private Link integrates with AWS Marketplace and the multi-account access model. There are three distinct layers shown here. The top layer is the provider account, which contains the network load balancer pointing to the back-end EC2 service instances. The provider creates an endpoint service resource that wraps the NLB and is published through the marketplace. The middle layer represents the AWS Marketplace directory. When a provider lists their service, the marketplace entry includes the service name, which takes the form of a service endpoint name that consumers reference when creating their interface endpoint. Consumers discover available services through the marketplace catalog and initiate a subscription, which triggers the private link connection request. The bottom layer represents multiple consumer accounts. Each consumer account creates its own interface endpoint in its own VPC, referencing the provider's service name. Each interface endpoint gets its own set of ENIs with private IPs from that consumer's VPC subnet. This means the provider can serve thousands of consumer accounts through a single NLB-backed endpoint service, without any VPC peering or network-level trust relationships between the provider VPC and each consumer VPC. AWS also allows private link connections to span AWS regions using inter-region private link, though the interface endpoint must be created in the same region as the provider's endpoint service by default. Cross-region connectivity requires additional routing through transit gateway or similar constructs. Azure Private Link-DNS Integration and Approval Workflow. Azure Private Link has a particularly well-developed DNS integration story that sets it apart from both GCP and AWS in terms of operational automation. Understanding how Azure handles DNS for private endpoints is critical because getting DNS wrong is the single most common cause of private link failures in production environments. When a consumer creates a private endpoint for a service in Azure, they have the option to integrate with an Azure Private DNS Zone. Azure maintains a set of predefined private DNS zone names for its managed services. For example, the private DNS zone for Azure Storage is privatelink.blob.core.windows.net. For Azure SQL it is privatelink.database.windows.net. and for Azure Key Vault it is privatelink.vaultcore.azure.net. When the private endpoint is created with DNS integration enabled, Azure automatically creates a record in the appropriate private DNS zone, mapping the service's FQDN to the private endpoint's private IP address. The diagram shows this DNS resolution flow. A consumer virtual machine initiates a DNS query for a service like myaccount.blob.core.windows.net. The query first hits the Azure-provided DNS resolver in the consumer VNet. The resolver checks the private DNS zone configuration linked to the VNet. Because a private DNS zone for privatelink.blob.core.windows.net is linked to the consumer VNet, the resolver returns the private endpoint's private IP rather than the public IP that would normally resolve for that host name. The consumer virtual machine then connects to the service using this private IP, and the connection flows through the private endpoint's network interface to Azure's backbone and then to the storage service. On the approval side, Azure Private Link supports both auto-approval and manual approval through Azure's role-based access control and resource policy framework. The provider can configure which subscriptions, resource groups, or specific resource IDs are auto-approved, and all other connection requests are queued for manual review through the Azure portal or API. The connection states in Azure are pending, approved, rejected, and disconnected, closely mirroring Google CP's model. Feature comparison. GCP PSC versus AWS Private Link versus Azure Private Link. Now that we've examined each platform's architecture in detail, let's bring the comparison together in a structured feature matrix. This slide covers the most operationally significant dimensions across the three implementations. On the load balancer requirement, Google GCP PSC supports both internal TCP/UDP load balancers and internal HTTP/HTTPS load balancers as backends for service attachments, giving producers flexibility in how they expose Layer 4 and Layer 7 services. AWS Private Link exclusively requires a network load balancer, which means producers must go through an NLB even if they ultimately want Layer 7 routing behavior, adding cost and complexity. Azure Private Link requires an internal standard load balancer, which supports both TCP and HTTP workloads but must be the standard SKU, ruling out basic load balancers commonly found in older environments. On DNS automation, Azure leads here with automatic private DNS zone record creation when DNS integration is enabled at endpoint creation time. AWS provides DNS hostnames automatically for interface endpoints and supports private DNS with a VPC setting enabled, though the experience is less seamless than Azure for custom service names. GCP requires manual cloud DNS configuration by the consumer, offering the most control but the least automation. On Google API access via PSC, Google CP uniquely allows consumers to route traffic to Google-managed APIs like Cloud Storage and BigQuery through PSC endpoints, keeping that traffic on Google's private backbone. Neither AWS nor Azure offers an equivalent mechanism under the same private connectivity framework. AWS uses gateway endpoints and VPC endpoints for its managed services, and Azure uses service endpoints or private endpoints for its managed services under the same private link brand, but the unified approach in Google CP is architecturally cleaner. On cross-region support, AWS supports cross-region private link in preview. GCP PSC is regional by design, and Azure Private Link is also regional, requiring global VNet peering or other mechanisms for cross-region access. All three platforms support inter-organization and cross-account private service consumption, which is fundamental to the commercial software as a service delivery use case. GCP PSC for serverless and Kubernetes workloads. Google CP Private Service Connect is not limited to virtual machine-based workloads behind internal load balancers. It extends naturally to two of Google CP's most important compute platforms, Google Kubernetes Engine and Cloud Run. Understanding how PSC integrates with these platforms is essential for organizations running modern containerized applications that need to consume private services or need to be consumed privately by other teams. For GKE, Private Service Connect can be used in two directions. First, GKE workloads running in a private cluster can create Private Service Connect endpoints to consume third-party or internal services privately. The Private Service Connect endpoint is provisioned in the GKE node VPC, and workloads access it just as they would any cluster internal service, often through a Kubernetes service with an external name pointing to the Private Service Connect endpoint IP. Second, the GKE control plane itself can be accessed via Private Service Connect. When you enable Private Service Connect for the GKE cluster's control plane, the Kubernetes API server is accessible through a Private Service Connect endpoint in your VPC, eliminating the need for the control plane to have a public IP address at all. This is the recommended pattern for private GKE clusters in regulated environments. This diagram shows both patterns. The GKE private cluster contains the GKE node pool from which application pods run. Those pods connect to a PSC consumer endpoint within the same VPC to reach a partner service through its service attachment. Simultaneously, the cluster admin connects to the GKE control plane via a separate PSC endpoint, meaning the Kubernetes API server never exposes a public endpoint. Both paths remain entirely on Google's private network, and no public IPs are required anywhere in the architecture. For Cloud Run, PSC enables private ingress to Cloud Run services by allowing a PSC endpoint to front a Cloud Run service's internal load balancer. This means a Cloud Run service can be consumed by other VPCs without exposing an HTTPS endpoint on the public internet, which is particularly valuable for internal microservices architectures where Cloud Run is used as the runtime but the service should not be publicly reachable. AWS Private Link Provisioning a Custom Endpoint Service. Understanding the exact steps to provision a custom endpoint service on AWS helps clarify the operational model and the responsibilities of the service producer. Let's walk through this configuration code block sequentially, covering every parameter. The first command uses the AWS CLI to create a VPC endpoint service. The Network Load Balancer ARNS parameter specifies the ARN of the network load balancer that will receive traffic from consumer interface endpoints. This is a required parameter, and the NLB must already exist and be active. Only NLBs in the same region and account are supported here. The acceptance required flag is set to true, which means connection requests from consumers will not be auto-approved. The producer must explicitly accept each one. Setting this to false enables auto-acceptance. The private DNS name parameter allows the producer to associate a custom domain name with the endpoint service. So consumers who enable private DNS for their interface endpoint will resolve that domain to the ENI's private IP automatically. This requires the producer to verify domain ownership via a TXT record in their public DNS. The Tag Specifications parameter adds resource tags for billing attribution and resource organization. The second command modifies the endpoint service permissions to allow a specific AWS account to connect. The service ID refers to the endpoint service ID returned from the creation command, which takes the form VPC-SBC-XX. The Add Allowed Principals parameter accepts a list of IAM principal ARNs. Using ARN:AWS:IAM::: account ID: root grants access to all IAM identities within that account. You can also specify specific IAM roles or users if finer-grained access control is needed. The third command creates the interface endpoint on the consumer side. The VPC ID specifies the consumer VPC. The service name is the service endpoint name provided by the producer, which takes the form com.amazon.aws.vpce.region.vpcesvcxxxxxxxx or a custom private DNS name if configured. The VPC endpoint type interface distinguishes this from a gateway endpoint. The subnet IDs list determines which subnets get ENIs. Specifying multiple subnets provides multi-AZ redundancy. The security group IDs control inbound and outbound traffic to the ENI, acting as a firewall at the endpoint level. The private DNS-enabled true flag activates private DNS resolution so the service's hostname resolves to the ENI IP within the consumer VPC. Pricing model comparison. Pricing is a practical dimension that significantly influences architectural decisions, particularly at scale. Each cloud provider has a distinct pricing model for their private service connectivity offering, and the cost structure can vary by several orders of magnitude depending on workload characteristics, for example, the ratio of data transfer volume to the number of endpoints deployed. For Google CP Private Service Connect, pricing has two components. The first is an hourly charge per PSC endpoint, billed per forwarding rule created in the consumer project. As of current pricing, this is approximately $0.01 per hour per endpoint, which amounts to roughly $7.30 per endpoint per month. The second component is a data processing charge applied to traffic flowing through the endpoint, charged at approximately $0.01 per gigabyte in the same region. There is no charge on the producer side for the service attachment itself. Cross-region PSC traffic incurs additional inter-region data transfer charges at standard Google CP rates. For AWS private link interface endpoints, pricing also has two components. The per AZ hourly charge is approximately $0.01 per AZ per hour. If you deploy an interface endpoint in 3 AZs for high availability, you're paying 3 times the per endpoint rate, which comes to approximately $21.90 per month for a 3 AZ endpoint. The data processing charge is approximately $0.01 per gigabyte. Because AWS's recommended pattern is to deploy endpoints in multiple AZs, the effective monthly cost per service endpoint is higher than GCP's model when HA is required. Gateway endpoints for S3 and DynamoDB remain free. For Azure Private Link, the private endpoint pricing structure includes an hourly rate per private endpoint of approximately $0.01 per hour, plus an inbound and outbound data processing charge of approximately $0.01 per gigabyte. Azure also charges for the private link service resource on the producer side, unlike GCP where the service attachment is free. The private link service hourly charge is approximately $0.01 per hour. This means Azure is the only provider that charges both the producer and the consumer, which has implications for internal platform teams that publish services consumed by many product teams. Observability and troubleshooting. When private connectivity breaks, the troubleshooting tools and signals available on each platform determine how quickly engineers can diagnose the root cause. Each cloud provider surfaces different telemetry for private service connectivity, and understanding what's available before you need it is essential for building reliable systems. On Google CP, the primary observability tools for PSC are VPC flow logs and cloud logging. VPC flow logs can be enabled on the subnet containing the PSC endpoint, capturing sampled connection records including source IP, destination IP, protocol, bytes, and packets. Because PSC performs NAT, the flow logs on the consumer side show the PSC endpoint IP as the destination, while flow logs on the producer side show the NAT translated IP. Google CP also exposes PSC connection status through the Cloud Console and the G-Cloud CLI, where you can query the status of each endpoint and its associated service attachment. Connectivity tests, part of the Network Intelligence Center, can validate whether a PSC endpoint should be reachable from a given source based on firewall rules and routes, without sending actual traffic. On AWS, interface endpoints can have VPC flow logs captured at the ENI level, which is the most granular capture point. AWS private link metrics are available in CloudWatch, including bytes processed per endpoint, packets processed, and active connections. though connection-level logging requires additional configuration at the application layer. AWS also provides endpoint-specific DNS names for each interface endpoint, including AZ-specific DNS names, which can help diagnose routing anomalies where cross-AZ traffic is generating unexpected data transfer costs. On Azure, private endpoint observability uses Azure Monitor, NSG flow logs on the private endpoint subnet, and Azure Network Watcher. Network Watcher's connection monitor can proactively test reachability from a source virtual machine to a private endpoint IP and alert on failures. Azure also provides a private endpoint DNS configuration diagnostic that verifies whether the private DNS zone is correctly linked and the A record resolves to the expected private IP. This is particularly valuable because DNS misconfiguration is by far the most common cause of Azure private link failures in practice. GCP PSC, provisioning with G-Cloud CLI. Let's examine the complete Google Cloud command line interface workflow for provisioning a PSC service attachment on the producer side and a PSC endpoint on the consumer side. Understanding the exact commands and parameters clarifies the operational steps and the relationship between the resources. The first command creates a forwarding rule in the producer VPC, which is the Google CP resource that front-ends an internal load balancer and makes it referenceable by a service attachment. The load balancing scheme equal operator internal flag specifies this is an internal-facing forwarding rule, as opposed to an external one. The backend service parameter references the backend service resource that contains the MIG or NEG serving the actual application. The ports equal operator 443 specifies that this forwarding rule accepts traffic on TCP port 443, which the service attachment will forward to consumers. The region parameter is required because PSC is a regional resource. The subnet parameter specifies which subnet's IP range the forwarding rule's internal IP is allocated from. The second command creates the service attachment itself. The producer forwarding rule parameter references the forwarding rule created in the previous step. This is the link between the service attachment and the actual service backend. The connection preference equal operator accept underscore automatic flag configures the service attachment to auto-approve all incoming PSC endpoint connection requests. Changing this to accept underscore manual enables explicit approval. The NAT subnets parameter specifies one or more subnets in the producer VPC that PSC will use for NAT. IPs from these subnets appear as the source when producer-side services log incoming connections from consumers. The region must match the forwarding routes region. The third command creates the PSC endpoint in the consumer project. The network and subnet parameters specify where the endpoint's private IP is allocated. The address parameter references a reserved internal IP address, which becomes the consumer-facing PSC endpoint IP that applications connect to. The target service attachment is the full URI of the producer's service attachment, obtained from the producer's service documentation or marketplace listing. The region must match the region of the target service attachment, since PSC is strictly regional. Choosing the right private connectivity solution. After examining all three platforms' private service connectivity implementations in depth, the natural question is, which solution should you choose and when? The answer depends on a combination of your primary cloud platform, workload type, compliance requirements, cost sensitivity, and operational maturity. Let me walk through a decision framework that covers the most common scenarios. If your organization runs primarily on GCP, Private Service Connect is the natural choice and should be the default for any inter-project or inter-organization private service consumption. PSC's biggest differentiator is the unified access to Google-managed APIs, which eliminates the need for separate mechanisms to keep storage, analytics, and messaging traffic off the public internet. The manual DNS step is a drawback compared to Azure, but it's a one-time operational task that can be automated with Terraform or Deployment Manager. PSC is also the correct mechanism for securing GKE control plane access in regulated environments. If your organization runs primarily on AWS, private link interface endpoints are the standard for private service consumption. The key architectural decision is managing endpoint sprawl in large accounts with many services. The per availability zone hourly cost of interface endpoints adds up quickly. Organizations should evaluate whether gateway endpoints can serve S3 and DynamoDB traffic to reduce cost, and whether a centralized VPC endpoint sharing model via AWS Resource Access Manager reduces the number of endpoints that need to be deployed per spoke VPC. If your organization runs primarily on Azure, private link with private endpoints is clearly superior to service endpoints for regulated workloads because it keeps traffic entirely within the private network. The automated DNS integration is Azure's strongest operational advantage, significantly reducing the risk of misconfiguration. Organizations should plan their private DNS zone strategy carefully at the outset, as the zone topology is difficult to restructure once established across a large VNet hierarchy. This comparison table summarizes the decision criteria across 6 key dimensions, mapping each dimension to the platform that offers the strongest implementation. Use it as a starting point for scoping your private connectivity architecture, then validate against your specific workload requirements and cost models. Terraform provisioning. GCP Private Service Connect. Infrastructure as code is the standard for provisioning private connectivity resources in production environments. Manually creating PSC endpoints, service attachments, and DNS records through the command line is acceptable for learning. But at scale, these resources need to be managed through Terraform so that they are version controlled, reviewable, and reproducible across environments. Let me walk through the Terraform configuration for GCP PSC from producer to consumer. The first resource block defines the Google Compute Forwarding Rule for the producer side. The name field is the resource label that appears in the GCP console. The load balancing scheme is set to internal, which constrains this to internal traffic only. External forwarding rules would use external or external manage. The backend service argument references a data source that looks up an existing backend service by name, avoiding hardcoding resource IDs. The ports list specifies which TCP ports this forwarding rule listens on. The region field must be consistent across all PSC resources in this configuration. The subnetwork field allocates the forwarding rule's internal IP from the specified subnet's address range. The second resource block defines the Google Compute Service Attachment, which is the GCP native resource type for APSC service attachment. The producer forwarding rule argument references the self-link of the forwarding rule defined above, creating an explicit Terraform dependency between the two resources. The connection preference of accept automatic means all consumer endpoint requests are approved without manual intervention. The NAT subnets argument references a list of subnet self-links. Terraform uses a data source lookup here to retrieve the subnet resource by name. The reconcile connections argument, when set to true, tells GCP to automatically reconcile stale connections if the NAT subnet configuration changes. The third resource block defines the Google Compute Forwarding Rule on the consumer side, which is how GCP represents a PSC endpoint in Terraform. Note that this uses the same resource type as the producer's forwarding rule, but with load balancing scheme left empty, which signals to GCP that this is a PSC consumer endpoint rather than a standard internal load balancer forwarding rule. The target argument is set to the service attachment's self-link, which is the critical link between consumer and producer. The IP address references a reserved static internal IP that will become the private endpoint IP that consumer workloads connect to. Terraform provisioning a Azure Private Link. Azure's Terraform provider for private link involves 3 distinct resource types that must be provisioned in a specific order. The private link service depends on the load balancer. The private endpoint depends on the private link service, and the private DNS zone configuration depends on both the private endpoint and the VNet. Let me walk through this configuration in order. The first resource block defines Azure_private_link_service on the producer side. The load_balancer_frontend_IP_configuration_IDs argument is a list referencing the front-end IP configuration IDs of the producer's standard internal load balancer. This is the Azure equivalent of the Network Load Balancer ARN in AWS's model. The NAT_IP_configuration block defines the subnet from which NAT IPs are allocated when consumer traffic enters the producer VNet. The primary argument in this block marks one NAT configuration as the primary one when multiple are defined. The auto_approval_subscription_IDs list specifies which consumer subscription IDs are automatically approved without requiring manual acceptance. The second resource block defines Azure private endpoint on the consumer side. The subnet ID argument specifies the subnet where the private endpoint NIC is created and allocated its private IP. The private service connection block is the key configuration that links the consumer endpoint to the producer service. The private_connection_resource_id references the ID of the producer's private link service, establishing the connection. The is_manual_connection argument controls whether the connection request requires manual approval, setting it to false requests auto approval based on the producer's auto_approval_subscription_IDs configuration. The request_message field is a human-readable string that appears to the producer when reviewing the connection request, useful for identifying which consumer team is requesting access. The third resource block defines Azure_private_DNS_zone and Azure_private_DNS_zone_virtual_network_link. The private DNS zone name must match the predefined zone name for the service type, for example private_link.database.windows.net for Azure SQL. The virtual network link resource associates the private DNS zone with the consumer VNet, enabling DNS queries from virtual machines in that VNet to be resolved using the private zone records. The Azure_private_DNS_record resource creates the actual record mapping the service host name to the private endpoint's private IP address, which is retrieved from the private_endpoint resource's private_IP_address output. AWS Private Link-ECS, Lambda, and serverless targets. AWS Private Link is not limited to EC2-based backends. AWS has progressively extended private link support to serverless and container-native targets, which is significant for organizations building microservices architectures on ECS Fargate or Lambda. Understanding the integration path for these targets helps architects design private connectivity for modern application patterns without forcing a return to virtual machine-based infrastructure on the producer side. For ECS Fargate, the integration path uses an application load balancer or network load balancer in front of the Fargate tasks. Since private link requires an NLB on the endpoint service side, the most common pattern for ECS targets is to front the Fargate service with an ALB for layer 7 routing. Then place an NLB in front of the ALB using a TCP listener that forwards to the ALB's IP addresses. This NLB then backs the endpoint service. An alternative pattern uses ALB with IP-based target groups directly registered as NLB targets, removing the double load balancer complexity. AWS announced native ALB-backed private link support, which simplifies this significantly when available in the target region. For Lambda, the integration path uses a Lambda function URL or an API gateway private endpoint. Lambda function URLs with private link support are accessed via interface endpoints for the Lambda service itself. Consumers create an interface endpoint for the COM. Amazon AWS.region.lambda service, which enables private invocation of Lambda functions without traversing the public internet. For Lambda-backed AP is API Gateway private endpoints create an interface endpoint for API Gateway in the consumer VPC, and traffic to the private API flows through this endpoint to API Gateway's regional infrastructure, which then invokes the Lambda function internally. This diagram shows both serverless patterns. The consumer VPC contains interface endpoints for both Lambda and API Gateway service names. The Lambda interface endpoint connects through AWS infrastructure to the Lambda function in the producer account, enabling private function invocations. The API Gateway interface endpoint connects to API Gateway Private REST API, which is configured with a resource policy that restricts invocation to only traffic arriving through the interface endpoint VPC endpoint ID. API Gateway then invokes the Lambda function internally within AWS's private network, completing the fully private request path. Performance and bandwidth limits. Private service connectivity solutions introduce network hops and NAT translation that do not exist when services communicate directly within a VPC. Understanding the throughput limits, latency characteristics, and scalability constraints of each platform's implementation is essential for capacity planning and for evaluating whether private connectivity is viable for high bandwidth or latency-sensitive workloads. For Google GCP Private Service Connect, the throughput is limited primarily by the backend internal load balancer's capacity. Google GCP internal TCP/UDP load balancers support up to 1 gigabits per second per backend instance by default, but can scale to much higher aggregate throughput by adding backend instances. The PSC forwarding rule itself does not impose an explicit bandwidth cap. Google documents that PSC scales with the underlying load balancer. Latency added by PSC is minimal, typically sub-millisecond within the same zone, because Google GCP's Andromeda Network virtualization layer handles the NAT translation in the hypervisor fabric without additional hops. For AWS Private Link, the interface endpoint scales automatically, and AWS documents that Private Link supports bandwidth up to 10 gigabits per second per availability zone per endpoint by default, with bursting up to 40 gigabits per second. This is substantially higher than the per-instance limits in GCP's model and makes Private Link suitable for high-throughput data pipeline scenarios. Latency added by Private Link is documented as sub-millisecond within the same AZ. Cross-AZ traffic through Private Link adds standard cross-AZ network latency and incurs data transfer charges, which is why AWS recommends deploying interface endpoints in each AZ used by consumer workloads. For Azure Private Link, Microsoft documents throughput limits of 1 gigabits per second per Private Link service by default, with the ability to request higher limits. The private endpoint NIC itself supports up to the bandwidth of the virtual machine SKU it is attached to, but the Private Link service NAT path is the constraining factor. For very high throughput requirements, Azure recommends creating multiple Private Link services backed by separate load balancer front-end IPs and distributing consumer traffic across multiple private endpoints. Latency characteristics are similar to GCP and AWS. Sub-millisecond within the same region when both producer and consumer resources are in the same Azure region. Compliance and regulatory considerations. Private service connectivity is not just a networking optimization, it is a compliance requirement in many regulatory frameworks. Understanding how GCP PSC, AWS Private Link, and Azure Private Link satisfy specific compliance controls helps security architects build the evidentiary record needed for audits and certifications. Under PCI DSS requirements, cardholder data must not traverse the public internet unencrypted, and network segmentation must be demonstrable to auditors. Private service connectivity satisfies the network segmentation control by ensuring that traffic between payment processing services and their dependencies never crosses a public network path. Auditors can examine VPC flow logs or NSG flow logs to confirm that no traffic to service endpoints traverses an internet gateway or public IP. On GCP, The combination of PSC and VPC service controls creates a particularly strong posture for PCI DSS because VPC service controls can enforce that specific Google APIs are only accessible from within a defined perimeter, and PSC ensures the access path is private. Under HEPA requirements, protected health information must be transmitted only over secure channels, and cloud providers must sign business associate agreements. All three cloud providers sign BAAs, and private service connectivity strengthens the technical safeguard posture by eliminating the public internet as a transmission path for PHI. AWS Private Link is specifically called out in AWS's HEPA compliance guidance as the recommended mechanism for accessing AWS services that process PHI in a HEPA-eligible workload. Under SOC 2 Type 2 requirements, the availability, confidentiality, and processing integrity of data must be demonstrable over time. Private service connectivity contributes to the availability control by providing a deterministic, low-latency network path without the variability of public internet routing. It contributes to the confidentiality control by ensuring data does not traverse shared public infrastructure where packet-level interception is theoretically possible. The logging requirements under SOC 2 are satisfied by VPC flow logs on all three platforms, which provide time-stamped records of private connectivity flows that auditors can examine. Series wrap-up and key takeaways. We have now covered the complete landscape of private service connectivity across GCP, AWS, and Azure. From foundational architecture through production hardening, compliance positioning, and infrastructure as a service provisioning. Let me summarize the key takeaways from this series that should guide your architectural decisions. The first takeaway is that all three platforms solve the same fundamental problem: private service consumption without VPC peering, but they differ meaningfully in their operational models. Google GCP PSC's manual DNS step is its biggest operational friction point but gives the most control. AWS Private Link's NLB-only requirement is a meaningful constraint for producers wanting Layer 7 native exposure. Azure Private Link's automated DNS integration is a genuine operational advantage that reduces the risk of misconfiguration. The second takeaway is that GCP's unified treatment of Google-managed APIs under the PSC framework is architecturally distinctive and has no equivalent on AWS or Azure under a single mechanism. If keeping traffic to managed storage, analytics, and messaging services off the public internet is a priority, GCP's approach is the most cohesive. The third takeaway is that cost management requires deliberate architecture. AWS's per-AZ interface endpoint pricing creates endpoint sprawl costs that are easy to underestimate. Use Resource Access Manager endpoint sharing aggressively. Azure's dual-side billing for both private link service and private endpoint requires platform teams publishing services to factor producer-side costs into their service costing model. GCP's producer-side free service attachment is a meaningful advantage for internal platform teams serving many consumers. The fourth takeaway is that DNS is always the first thing to verify when private connectivity fails. Build DNS validation into your deployment pipelines and monitoring. Before any application team declares a private endpoint or PSC endpoint operational, a DNS resolution test from within the consumer network should confirm that the service fully qualified domain name resolves to the expected private IP, not a public IP. This single check prevents the majority of production incidents related to private service connectivity. Thank you for your attendance. Please consider subscribing to the channel and liking this video.